After heavy dinner with wine and so on, I applaud the enthusiasm of those early birds here. And well, this session will begin with a talk by Alejandro Ayala, whom I thought a theorist, but now he's now going to talk to us about the multi-purpose detector. I believe in NICA, no? Well, welcome, Alejandro.
Thank you. Yes, it is very much appreciated that after wine and dancing and night dinner, you guys decided to come here early. So I hope not to disappoint you. And what I want to do is to tell you of my and my group's recent involvements in this effort, which is the MPD collaboration, the multi-purpose detector, at the NICA complex in Dubna, in the Joint Institute for Nuclear Research. Here, thanks. And so why is this an important experiment? Well, as we all know, nuclear physics and nuclear matter is the interactions are manifested or driven by strong interactions, and quantum chromodynamics is the fundamental theory of those interactions that describes those interactions. And as we know, under ordinary circumstances, what we observe are quarterless particles. But the idea is to try to see whether compressing or heating up nuclear matter, we produce the state of matter that has been dubbed the quark-Coulomb plasma. And this can be achieved, of course, by putting in a lot of energy in nuclear collisions, heavy ions, or this existed in the early universe, or it is speculated that also exists in the core of neutron stars. So for that purpose, there are many facilities around the world that have been exploring this state of matter. And one of them is this nucleotron ion collider facility, NICA, which is near completion in Dubna. And this is an aerial picture taken a few weeks ago. And it consists of course, the nucleotron, which is the main booster here, or the booster complex, and then the collider ring here. And two experiments are envisioned. One of them is the multi-purpose detector right here. There is another one which is going to be devoted for spin physics, and it's still being constructed, and the spectrometer is still being constructed. But I will concentrate on describing the MPD. Now, just to put it in perspective, we know that from the old days of the Bevelac and AGS, collisions of heavy nuclei were achieved at energies which are barely relativistic, and these are the energies in the center of mass per pair of colliding nuclei. And then this story continued, and then in CERN, the SPS achieved collisions of order 20 GeVs per nucleon, again, the nucleon pair in the center of mass. And then it came break, and as we know, LHC, which is has an energy of order 5 TeVs for these kind of collisions. But then, although this program was very successful, and in particular, these three facilities were able to show that something like a quark-Coulomb plasma was produced in these kind of collisions, it was realized that in order to study deeper into the phase diagram of QCD, we needed to come down to smaller energies, because there, nuclear matter is stopped or has a stopping power which is larger, and therefore we have a chance to create denser nuclear matter. And if we have denser nuclear matter, we also have larger baryon chemical potential, and then the phase diagram, the temperature versus baryon chemical potential can be explored deeper. And this is what I want to show you here. This is the realm of CERN and RIC experiments. And of course, many interesting achievements have been reached. For instance, there are many signals that show that a deconfined state of matter is produced with chiral symmetry restoration properties. But if we want to explore deeper, then we need to come down in temperature and increase the baryon density and see whether somewhere in this region we can infer the properties of this matter, in particular by locating this critical endpoint right here, where the crossover transition becomes first order. We want to see how strong this first order transition is, if it exists, and where the chiral symmetry restoration and confinement transitions decouple. So all of this is what we want to explore. There are several facilities that will be doing that. And in particular, the beam energy scan in CERN has been doing it with interesting results. But I will be concentrating on describing to you what are the capabilities of the MPD. Just to make a bridge with what is now currently being dubbed as multi-messenger physics in this business. If we explore deeper into the phase diagram at small temperature, which can be perhaps achieved by inferring the properties of objects like this, these compact objects like neutron stars, then of course we will have a better description of the phase diagram. And what I want to emphasize is that NICA is a bridge between this physics in heavy ion collisions and the physics in compact objects. Okay, so what is the multi-purpose detector? It's a spectrometer, which is the usual kind of spectrometers. You can see here the characteristics, the length, the gas that will be used for the TPC. And it is made out of these main detectors: the TPC for charge particle tracking, the time of flight, the electromagnetic calorimeter for PID for electromagnetic probes, and the fast forward detector and the forward hadron calorimeter. And eventually, in a second stage, we will install also the internal tracking system. These are this is the coverage in pseudo rapidity for each one of these detectors. And this is the subsystem status of the production of these subsystems. You can see that many of them have achieved already some important goals. And later on, I'll show you what is the current status and schedule for data taking. Now, what we realized a few months ago is that the nominal luminosity here, written in terms of the rate of collisions as a function of the collision energy, was put MPD NICA energies at a competitive rate, but only for the largest energies that we envision to collide. And so this luminosity dropped down rather fast for collision energies, which are on the ballpark of what we infer can be the interesting region to locate the critical endpoint. So the collaboration decided to also start taking data in the fixed target mode. And so some studies have been done, and some of them are still being done. But the idea is to locate here a tungsten wire and then aim to it the beam, well, from here to the left, and then use the TPC and the rest of the detectors as in the fixed target mode. With that, then we achieve a higher rate and therefore become more competitive with other experiments in this region, which are also fixed target, and expect to have results, physics results sooner. This is the collaboration activity. We recently submitted the first paper of the collaboration where we described all of these subsystems and the physics capabilities. And a second collaboration paper describing the status, the current status is being prepared. Just want to mention that this I managed to convince the collaboration to submit the second paper to the Mexican Journal of Physics, and it is currently in preparation. This is the physics program, and I'm not going to go through all of details. In fact, what I'll do is to show you some examples of the capabilities of our detector. And of course, we have the global observables, the spectra of light flavor and hypernuclei, correlations and fluctuations, spectroscopies here, electromagnetic probes, KB flavors. And so it's basically, it covers all of the aspects of probes that can be detected in this kind of environment. And let me just quickly tell you what these capabilities are, for instance, or what is the motivation. So for instance, if we want to measure global observables at large baryon chemical potential, we know that there is very interesting physics that is being already unveiled, particularly in the beam energy scan program. Because see, what we can do is to look at the fluctuations measured in terms of the kurtosis of the statistical fluctuations in several observables, for instance, in proton number as a proxy of baryon number. So, for instance, we know that if this kurtosis is flat, nothing interesting other than the hadron gas is describing the system. But as we lower the energy and increase the baryon density, then what we find, or what it's found, is that this flat behavior stops being true, and then the kurtosis comes down, and then eventually goes up, and then comes down again, as measured by Hades here. So this transition region is rather interesting because it shows that something is happening in this region, and perhaps, although very difficult to read because of the large statistical fluctuations, we may be reaching the position of the critical endpoint in this energy region. And of course, NICA and MPD aim to provide information in this region. So other interesting pieces of physics that can be explored is in terms of, for instance, this is a cartoon that represents a peripheral collision where we know that large magnetic fields or even large angular momentum is produced. Some of the observables that have been associated with this magnetic field have to do with the chiral magnetic effect, and also we want to study that effect. Now, if we want to map the phase diagram, what we want is to have a model, and the model is at freeze-out, chemical and kinetic, provide the parameters that describe this freeze-out, and therefore how the phase diagram in temperature versus chemical potential is behaving as we move up or down in energy. And for that, the statistical model is used. And this is a collection of data from several experiments. We aim to also describe both the temperature versus the square root of the energy and the transverse velocity, also as a function of this energy, and fill in some gaps here in this energy region to see what is the trends in these parameters. Another interesting observable that we are doing work to describe, it has to do with the transferring of vorticity to spin, as I mentioned. In these peripheral collisions, this region, this interaction region has vorticity. It's rotating around. There is an angular momentum, and the question is how fast this angular momentum can be transferred to spin degrees of freedom, and how we can observe this transferring of spin degrees of freedom. And this should show us a polarization of certain particles. In particular, when we speak about polarization, these have to be spin 1/2 particles, and there are very interesting measurements that measure the polarization of lambdas and anti-lambdas, particularly STAR in the beam energy scan program has found this interesting behavior. There is a rising trend here when the energy goes down. And you can also study vector mesons. In this case, the spin observable is not the polarization, it's called the spin alignment. What we want to do is to measure extra points in this region where MPD can say something about. Okay, well, there is, of course, interesting capabilities to identify light hadrons. These are simulations that show that this spectrometer has these capabilities with large acceptance and a good resolution. I'm not going to stop very much describing this here. Also, hyperon reconstruction is being studied extensively, and we have capabilities to do that in several collision systems. Hadron resonances can also be reconstructed at the Monte Carlo level. This is, of course, the Monte Carlos have been passed through the material of the detector, and we are able to reconstruct and compare to Monte Carlo, and the comparison is very, very, very fair. And there are not, for these kind of measurements, not such a large statistics is needed. So this will be first-year physics. This is not the case for femtoscopy studies, because for these, unfortunately, we need a large statistical sample. But let me just tell you that what is the importance of this observable. We know that due to quantum correlations or final state interactions, the correlation of two particles shows this shape as a function of the relative momentum. So this is just a manifestation of Heisenberg's uncertainty relations. The smaller the size in this plot here in the horizontal axis, the larger the radius is. So they are inversely proportional. So the product is of order h bar. And so if we measure these correlations, we are able to infer the size of the system, the size of the fireball that was created in these collisions. And so we know that there are measurements. And in particular, there is a parameterization of these sizes. You can imagine that in a 3D collision, there are these different radii. They are called R side, long, and out. And these are the measurements for these observables that are known. And what we want to do is to also contribute to these measurements in this region, which is the region of the energy region where NICA operates. Just as an example that has been simulated, we have put in two different equations of state, one in red and one in green. And we know that this observable is sensitive to the equation of state. So when we have measurements in this energy range, we would be able to say whether or not there is some phase transition that is occurring. Also, MPD has a very large capability for photon and electromagnetic probes in general. And we know that this observable is related to the system temperature. So what we want to do is to measure the direct photons, which are known to carry information about the early stages of the collision. And if thermalization has been achieved, then the slope of this plot here, this is the yield, the photon yield as a function of PT. The yield here will be related directly to the temperature of the system. So we, of course, want to do these measurements, and we also want to do it with other electromagnetic probes. In particular, if we plot the lepton spectrum, we know that this has a very rich structure, and in the low mass region, this is sensitive to, for instance, the modification of the vector mesons in medium. We know that this is a phenomenon that occurs. So, for instance, rho becomes broader. So we want to confirm these measurements here in this region, and also make measurements in the intermediate mass region of the pair, and to also give an estimate. This is related directly to the temperature of the system. So we have that capability, and as an example, this is some collection of data. This is from BESS, and you see here that this region is not very well mapped. So what we want to do is to contribute with our capabilities to map better this region. Last, but it's not all. You can imagine that there are many other physics capabilities, but let me just tell you at the end that we also want to do charm studies. And for that, of course, we need tracking. And the internal tracking system is not going to be ready for the first stage, but it's being worked on for a long time already. So the idea is to have this technology based on maps, to have several layers of this detector material around the beam pipe. So currently we are thinking about 3 or 4, and then this will be placed here inside the TPC, and this internal tracking system, as you know, will be used to locate the vertex with a good accuracy, and some simulations show that this can be done indeed. Okay, so for the last part of the talk, I just want to take advantage of the fact that the group that I'm leading in MPD, the Mexican group, is also working in contributing with a detector, which is designed to contribute to the trigger of the TOF. And so this is called the mini beam counter, and mini BB for short. And it will be located here in the place where eventually ITS will be located. So this will be a detector that is just present for the first stage of the operation. And well, what we want is to contribute to the trigger, particularly in low multiplicity events, where the FHCAL or the FFD cannot do much. So we will locate it here in the central rapidity region, and we've been working together hand in hand with the ITS team to adapt the mechanical support and the electronics. What is this detector? Well, sorry for the quality of the picture, but what we have is these 2 electronic cards, which are attached to the sensitive elements of these detectors, which are plastic scintillators, which then have at the end points silicon photomultipliers that then transmit the signal to the PCB here. And then, of course, this is mounted in a mechanical structure. And these are the characteristics. Each module has 20 plastic scintillators. This is the company that provides them. It's aging. These are the dimensions. And as I said, each plastic is surrounded by 2 CPMs, and this is the series. And they are fixed to the PCB. And this is the dimension of the electronic boards. And then there's, of course, cold plates to dissipate energy, so on and so forth. It's a very interesting and challenging, although small, but challenging detector. So just to go to the final part of the talk, this is the collaboration. It is currently made out of 12 countries, more than 500 participants, 38 institutions, plus GINER. And this is the managing organization. And these are the institutions that are taking part in the experiment. As you can see, there is a large contribution from Mexico, the Michoacan University, the Metropolitan University, the Institute for Nuclear Sciences, the University of Sinaloa, and the University of Coulomb. And this effort has been going from a long time already. And this is a summary of the status and plan. So in about 2 weeks ago, the advisory committee, the project advisory committee got together, and they recommended a series of steps to be taken in such a way that we fulfill the schedule. In particular, this means that at the end of this year, we will be commissioning many of these detectors, and the installation will start. And for 2025, the idea is to have beams. And so that implies also working together with the accelerator department, which have provided with this schedule here. And they promise beams during spring. And then what we will do is to have the first attempts to inject beams in the collider, and then work with fixed target with this tungsten wire of this size. And the collisions will be taking place at the end of summer. And the bunches in the collider will be up to 2 × 10⁸. And the luminosity will be small. The planned largest luminosity we have set up for is 10⁻²⁸, 10⁻²⁷, 10⁻²⁸. But so this will be a small luminosity, but still it will be very interesting to see whether or not we can see collisions. Now, future plans depend, of course, on the performance on this stage. And so let me come to the summary. The MPD collaboration is steadily coming to final integration. And data taking will be hopefully taking place next year. The physics program for the first years of data taking has been formulated, and the first paper has been submitted. Another one is being prepared. And as I mentioned, and I hope that I could convince you, MPD will provide a unique opportunity for the investigation of properties of nuclear matter at maximal densities, to map the QCD phase diagram and to search for the cross transition and the critical endpoint. The first operation of the MPD detector is expected at the end of middle end of 2025, and we will start taking data in a fixed target mode. Thank you.
Hello. Thank you very much, Alejandro. You finished ahead of time. And so we are open for questions. Yes. So if you can put the third bullet from your summary. So I know that during your presentation, you tried to make contact with the cold equation of state, like for neutron stars. So what will be the impact of this program on constraining the equation of state of cold matter, let's say at t = 0 and large densities?
It is actually a very crucial question, because of course, this is terra incognita. Let me go back to the phase diagram cartoon. All of this is speculative. There's nothing. Well, there are guides, theoretical guides, but experimentally, this region has not been studied. Now, the question is what some guiding models can tell you about, for instance, temperature and baryon chemical potential, and whether or not you can extrapolate with certain confidence. Now, lattice QCD can be used, but not very far from the temperature axis because of the sign problem, as you know. So this is not the best guide. So other theoretical guides tell you that here there should be a first order phase transition, but experimentally it is very difficult and unlikely that this region will be reached. So if we are lucky and can locate through this analysis of fluctuations a critical endpoint which can be then translated into a set of variables such as mu, b, and t, then my expectation is that we are not going to go that far down our deep. So it is complicated to say that these experiments will say anything about it, but we can have complementary information if we use multi-messenger physics, as I mentioned. Leticia.
So thank you for the talk. So I was wondering, because you said that you're going to use a fixed target, because to increase luminosity, basically, right? Does it change the mapping between energy and baryon chemical potential? Does it change the hydro description of the system? What do you expect to be different? Because we are used to having two beams and so on.
No, the collisions themselves are the ones that drive the physics. So it doesn't matter. I mean, it can always be relativistically boosted, any frame, right? So in that sense, the physics is not going to be affected. The important characteristic of the fixed target mode is that well, according to our simulations, instead of the luminosity here mentioned as the interaction rate in hertz, instead of this interaction rate coming down so fast in the region where we think interesting physics may be happening, with the fixed target, you have more interactions. So that means that instead of aiming two beams, one to the other, and then at the beginning, at the beginning of the operation of any collider, aiming one beam to the other is a complicated business. So if we want to have data at the beginning while we understand how to tune the beams, it is better to have some wall there, which is not really a wall, it's just a wire 100 millimeters, micrometers wide. And so the beam can be aimed rather easily to that. And it has also the advantage that these detectors can operate in such a mode. So the TPC itself is used or can be used to detect all the products of these reactions in the forward direction, provided we put the wire here at the beginning of the TPC. So the physics is going to be the same. Hydro description, everything is going to be the same. It's just that we will have a larger rate.
Well, Osvaldo, Chiquitales here is.
I cannot hear you, Osvaldo. Can you wait for the microphone? It's my limitation. Old age, you see. But turn on the microphone, otherwise it's the same.
Okay. No, the question is on the phase transition, where you can mention that colors are fluidity, maybe a probably phase there.
Again, Osvaldo, sorry, I got distracted. Say that again.
No, I'm saying that you can have there the colors are fluidity in the phase, so that the latent heat in that region may tell you which kind of color superfluidity you have. But the question is that in neutron stars, the radius is not that long because the state of zero momentum will go over the full volume, but it's only 5 kilometers. So there should be really a compromise between density and volume. So do we have any comment on that? Or?
I'm not an expert. As a matter of fact, we have here at least one expert, if not two. Perhaps they can comment. But what I can say from the theoretical point of view, I totally agree with you. And of course, there is a lot of physics that is going on in this region. In particular, we know that the transitions, chiral symmetry, and the confinement may not be happening in the same place, that is in the same value of mu p, but that instead what they tell us, or what this difference tells us, that there is a different kind of matter that is being formed here, and it's called the quarkionic matter. Right, and so, of course, depending on how the pairing is done, because see, this is going to be the sort of matter that will be paired with color, flavor locking, or, you know, but this is theoretical speculation. See, it is very unlikely that an experiment like this or like any other will reach this region. It's going to be through gravitational waves studies, if at all. We can constrain the equation of state coming down here, and of course extrapolating, but not, this is not an experimentally achievable region in this kind of experiments.
Okay, there's another question here.
Can you hear me? Okay.
Yes.
So how large a chemical potential do you expect to achieve in these experiments? And how would it compare to the ones expected at FAIR or presented beam energy scan? Maybe you put in some picture, but I wasn't able to see.
Right. No, I went through very fast. Yes, it's somewhere here. It's on the order of 600 to 800 MeVs. So that means that in this region,
Baryon chemical potential,
baryon
right?
chemical
Not
potential.
quark. Okay.
No, baryon. And so that means that we're still far from here, which is speculated to happen at 1 GeV, say, right? So it's this region that's going to be the maximum, perhaps. And this will be achieved at the smallest collision energies.
Okay, I have seen no other hands. I have a question. Well, thanks for the talk. And this region of energy is very interesting for nuclei and anti-nuclei physics. You didn't mention it.
I of course knew that you were going to be the chairman, and I was debating whether or not to put it in. And so I decided, well, he's the expert anyway, so he will tell us eventually about this. And I just was worried about the time. Yes, absolutely. This is very, and we have a rich program that includes this.
Very good. Well, this afternoon I will point in my transparencies. But this is very good. Well, Alejandro, thank you very much.
Thank you very much.
And I call on Daniel Tapia Takaki, our good friend from Kansas University, beautiful campus in Kansas University. Now Daniel is gonna give us a talk about probing the nucleus and nucleons at high energy.
Okay, well, thank you so much to, Arturo for the introduction. Yes, Lawrence, is that a nice campus? You're welcome to, yeah, I really enjoyed it. Oh, yeah, that's right, the microphone. Yes, thank you.
Okay. Yeah. Okay, what about now? Okay, great. So, okay. Let's see here. Okay, so it's really a pleasure to be here at UNAM at the Facultad de Ciencias. And today I will discuss with you, I promise to say give you an overview of some of the selected results on the, probing the nucleons and nucleons using UPCs. And I just want to tell you that there are quite a lot of results that I won't be able to cover, but recently, this December, we had a conference in Playa del Carmen in Mexico, where I invite you to have a look also some of these, presentations where they cover basically the whole spectrum of the program, from nuclear physics to, particle physics and beyond the standard model. And but today I will focus mainly on nuclear physics QCD studies. And I think this cartoon that you see here illustrates some of the things that we're interested to do. Here you have in this picture these colliding ions that we have, for example, at RIC or at the Large Hadron Collider in Geneva, where we are, of course, colliding, but sometimes these ions can interact electromagnetically. And what happens is that you have a photon that is emitted from one of those ions, because this highly, these ultra-relativistic ions, they have this strong source of photons, quasi-real photons, and they interact, and you can have photon nucleon or photon nucleus interactions, right? And you can produce things like vector mesons, as you see here. And then what we want to study is the structure and the properties of these targets. And what you find here is that not only we can do that, but we can do a study as a function of the photon energy. And the idea is that when you go to the highest energy, we can prove, a very unique dynamic system that I will tell you in this talk. Okay, so first, a little bit about how this happens. So this idea that the relativistic particles, are they can be expressed as a source of photons is, of course, not a new idea. This been there for a long time, since Fermi and others that found that these electromagnetic fields can produce these quasi-real photons. And if you look at Lorentz factors about beta 0.98, if you look at the electric, at the magnetic fields that you see here, these pulses, they are, that's why we call it quasi-reals, because you can really identify the pulse here. And this is, of course, an exercise that you do in ICN-UNAM, the bicycle-Willian approximation to obtain the photon flux. Now, the reason why we want to do this at higher energies, or at RIG, in Brookhaven National Lab or at LHC, is that we can make these studies as a function of energy. And in particular, the Large Hadron Collider, the energies that we can reach are really high. So this happens usually in these ultra-peripheral collisions, because these ions, they are far apart, more or less like at least 2 times the distance of this impact parameter, as you see here. And the kind of variables of kinematics that we study are listed here. You have this K that indicates the photon energy of these collisions. And then we also want to study the properties given by this big X, the Bjorken X variable. And as a matter of fact, we can determine in some reactions or some configurations the photon energy and the Bjorken X that tell us about the properties of this system, very similar to what we have in deep inelastic scattering experiments. And for the case of the photon energy, here, what we find is that when we study gamma LED systems like gamma LED, we can reach energies of about 700 GeV that has never done before in other colliders. And even when we look at gamma-gamma, we can go to 4 teraelectron in proton-proton, which discovered a very unique kinematics. And also, if you translate this in terms of the Bjorken X, you find that the kinematics is very unique. I'll show you in a minute. Okay, so in summary, if I want to tell you, we want to study these ultra-peripheral collisions of photon precisely because we're using it to do a photon-photon or photon-proton or photon-nucleus interactions at the highest energy. And this is a kind of, there are many questions you can study, but one of them is that, as we heard, during this meeting and also on the first day on the EIC talk, we want to study the structure and the dynamics of hadrons. And we want to study, what does the proton really looks like? And for that, we have to, this process of UPC is a good tool to measure it at different kinematics at different energies. One of the topics that we have seen here in the presentation is the question of what happened with gluon matter or gluon saturated matter. That we know that at HERA, this has been a study that people have measured the momentum fraction of these partons, as a function of this X variable. And you see that when you compare the case of gluons to respect to the other quarks, this density for gluons increase very rapidly when you go to smaller values of X. And this is the case for the protons. And the question is that there must be some mechanism that will tame this growth of this gluon. And this is when the richness of QCD with these self-gluon interactions that is illustrated here in this process, this emission of gluons, of course, has to be mitigated or controlled. And this is done by considering, in general, that these gluon emissions and this gluon recon must have some kind of dynamical equilibrium to reach this saturation. And the kind of questions or physics questions that we're interested are listed here. One of the questions is that is this nonlinear QCD mechanisms that are responsible for this equilibrium? How would that actually happen? What is the trigger? What is the physics behind that triggers this saturation regime? And is it possible experimentally to measure the scale, the saturation scale when this is happening? And the other question, which is also very important, is there a state of matter formed by this gluon-saturated matter that has some kind of universal properties like the color glass condensate that Alejandro is an expert and others here. Okay, so one of the things that we have here is this, we want to study this diagram, that considers these X scales and the Q scale, and of course there is this transition when we go to lower values of X where this saturation happens, and precisely finding this scale is what is interesting, as I was saying. But the plots that I show you at the beginning is for protons, but for the case of nuclei, we expect that this should happen as well, and the scale when this occurs should be much faster than for protons because of this scaling here. And that's why in the case of nuclei, nucleus collisions, we're interested to look at this because there is perhaps more sensitivity experimentally to find this and measure it. Now, this is very interesting, but of course there are some caveats or some challenges that we have to try to characterize this low X regime. And one of them is that in nuclei, we also have, we have nuclear shadowing as well that has been measured experimentally. And this is an observation that happens for protons, for nuclei, and that is illustrated here when we compare the case of nucleus, the cross sections of the DS cross section of nucleons with respect to nucleons, or the case where there is no effect of free protons, and as a function of X, and even for relatively modest values of X of 10 to the minus 2, besides these other effects like EMC effect and shadowing, we have this anti-shadowing region that corresponds to this, suppression of this reduction of this cross-section, which is very similar to what you may expect also in the case of shadowing. So again, what is really behind this? What is the mechanisms that is responsible for this? And how is that related to gluon saturation is one of the questions that is very important. And it has consequences not just to understanding, but also practical consequences, because in the field of heavy ion physics, we want to study many of these nuclear effects that, the initial state of what we call this kind of initial state effects of the nucleons before interacting is very important for understanding the quark-gluon plasma evolution as well. Okay, now I want to say that now there are quite a lot of results from heavy ion physics, from this kind of studies, or DS measurements, and now in the community there are still interesting to measure all these phases, going from color transparency to shadowing, saturations, and perhaps like this symmetry. That's the kind of the things we want to measure. Of course, on our community, the best machine to look into this is the electron-ion collider, right? Because it has the capabilities to measure all of these features in great detail, and this was discussed on Monday. But the thing is that with the colliders that we have now, like the Large Hadron Collider or RHIC, we can still, already explore some of these processes, and there is some uniqueness, in particular for the LHC, the fact that we can go to the highest energy. And this is illustrated a little bit here, where you find this diagram again of the scale of Q versus X, and you can see that we can go even to 10 to the minus 6 with the current projections in the next couple of years, compared to, and we can cover a very interesting region and very unique that will not be even covered by the electron-ion collider. Now, there are many ways how to study these physics programs and these questions, but the approach that I'm particularly interested is at the moment is to look into photon-induced collisions, because that gives us some kind of DIS-like measurements where we can also control some of these kinematics, as I was telling you at the beginning. And here is the typical Feynman diagrams of these reactions, where you have a photon coming from this lead interaction that emerges as vector mesons, and we can study the energy of this interaction given by this W gamma P. We can study the momentum transfer of this target. Sometimes it breaks. And this photon that is produced here that converts into this dipole, we want to also vary the size of this dipole, because then we can explore or probe the proton of the nucleus. And for that reason, we try to study different vector methods to increase the sensitivity. One interesting thing of this program is that we can look all kinds of reactions, exclusive, semi-exclusive, inclusive processes. And in particular, most of the physics right now has been exclusive, but with the new data, it will be possible to go beyond. Okay, so there are a lot of experiments. I have working with the ALICE experiment and CMS, so I will tell you a little bit about both, but I cannot cover, of course, a lot of things. But let me tell you a little bit of a couple of measurements, okay, that this is kind of an old measurement, but we have new results. But I want to show you that one interesting thing is to measure the energy dependence of the cross-section of J-size mesons as a function of energy, and which is also translated, you can also convert this in as a function of X. And this is the measurement that HERA, in Germany, the HERA collider, the experiment H1 and Sirius explore, they reach up to about 300 GeV. But with the LHC, now we can cover both the low energy and the high energies. And this is from round one, but now, LHCb and ALICE has data that covers now the whole region. And the physics question that we want to study is that there are several models, the saturation model that predicts that when you reach the saturation at high X, this is, there should be a deviation from this power law grow, and that should be one indication of the nonlinear QCD phenomenon. Now, as I said, there are a lot of works in lead-lead collisions as well, because the effects are enhanced. And here you have, again, the cross-section for J size, a function of rapidity. And it's very interesting that here already, when you compare the data, showing these points to this blue dotted line, this corresponds to the case where you don't have any nuclear effects like shadowing or saturation or some modifications. And you can see that indeed we see a very strong changes that indicates that there is something happening here. This modification of non-QCD type evolution. And this has been computed in multiple ways. So this is a plot that shows similar to this shadowing plot that I showed at the beginning, that shows the ratio of these two quantities and as a function now of X. And with the, some of the, this is not the most recent data because I wanted to show you some of the points without, having a lot of points here. But what you find is that indeed the data follows the central value of the state-of-the-art nuclear PDF calculations. And this blue band that you see here is the current uncertainty from these calculations. And if you consider now in this model the data, you can see that it's already very well constrained. It goes from this blue to this orange one. Of course, there are some theoretical challenges and caveats, and there are now recently more next to linear uncertainties, but it gives you an idea of feeling about the power of this data to understand nuclear densities. Now, very recently, one of the challenges that we have when we want to study the energy dependence is to separate, to really know what is the energy of the photon. And that's not so easy because when you have lead-lead collisions, the photon can come from any of these two lead sources. And in some cases, in some kinematics, one of the photons corresponds to low energy photon and the other one corresponds to high energy photon. When you look at the most forward rapidities, most of the data corresponds to low energy photons, and you want to be able to distinguish that. So there are several proposals of how to do that in practice, but this is one of them that is very simple to understand. Here you have the cross-section of, for example, this J size, and this can be written as the photon flux multiplied by the cross-section of the going in the, let's say, in the positive hemisphere of the rapidity, and then the ones going in the negative rapidity. And the way to do that, the way to decompose this or to extract the solution is by looking into the emission of neutrons that accompany these events, because in this reaction, it's very likely that there will be a secondary independent electromagnetic production of neutrons. And what happens if you look at the neutrons emitted in these reactions? Here you show the flux as a function of impact parameter described by different nucleon configurations. So cases where you have no neutrons, or at least one neutrons, or more than one neutrons. And you can see here in these two plots, the high energy photons have this kind of spectra, and here the low energy looks very different. So you can use that for disentangle that, and it's very simple. You just solve this linear system that you take here the cross section and the ones that you measure for the different neutron configuration, and that actually has been done by CMS and Alice. And here you can see this cross section now for nuclei that for the first time is possible now to explore the whole range, from 220 GeV to 800 GeV in energy. And we see very interesting observations here. One is that when you have no nuclear effects, you see this blue band here on the growth, and it seems that the very low energy, most of the models that used to work before don't work very well, because at the moment the understanding is that the anti-shadowing region is also not well understood in this place, which is perhaps not surprising. But when you go to the low X region, the data already sees kind of an onset of shadowing or saturation. The data is yet not able to distinguish between the two models using this measurement, but we do see an onset of this growing the energy dependent, which is very exciting. And this can also be now expressed in terms of the nuclear suppression factor as a function of X, and you can see it here in a different way, presented the data compared by making the ratio what you have in nucleus with expectation for protons, and you see this growth, the trend that I was telling you. Okay, this is something that has been published recently, and I don't think I have a lot of time, but I will tell you a little bit, give you a little bit about an idea of other things that we are interested in very quickly. One is to look into measure the momentum transfer and probe the transverse profile of the target of the proton and the lead. And the reason for that is because saturation models or several calculations predict that, like in diffraction patterns, when you hit this target, you will find the diffracted patterns, the location of those diffracted peaks and the appearance of those peaks is very sensitive, not just to saturation, but also to comparing different saturation models that theorists have come up with. Just to give you this, to show you this more clearly, here you have the momentum transfer for the rho meson, and here for the J psi. Compare cases where it's no saturation and couple of saturation models. And you can see here that the diffractive peaks happen at different locations. And so measuring this, of course, it's very challenging for the rho. It's something that we can only do at the electron ion collider. But for the J psi, it will be possible to do that in the future. And we have done, CMS actually has the first study on this for rhos, and there seems to be already some interesting indication that the energy dependence have a very different behavior, but the data is still not there for full studies. As I said, for J psis, this is something that Alice has a nice measurement, but it's still not at the very good precision. It's kind of precision very similar to what has been measured at Hera, which is very surprising, but still we need to have more to go to this region. Now, I want to tell you some of the very recent measurements and why it's interesting on the incoherent events, because what I show you so far has been exclusive studies where the proton or the nucleus remains intact besides those neutrons that are produced. But it's possible to measure incoherent production, which is cases where the photon interacts with a single nucleon instead of the whole nucleus. And this is interesting because theories predicted that there are some event-by-event fluctuations and geometrical fluctuations of the target that you see here. And the presence of these fluctuations tell you how round is the target. And again, this is sensitive to some, not just the geometry, but also saturation effects. And the way to understand to this is that the cross-section for incoherent can be expressed in the good Walker approach as the variance of these amplitudes. And when you have incoherent reactions, this incoherent term is very important and makes the dependence of the momentum transfer to be very different for round protons or no fluctuations, which is here, and with the ones with fluctuations. So this is something that, that has been measured very recently by Alice, that here you see the momentum transfer for these incoherent events compared to, okay, a lot of models here. But what you find is that when you go to the highest values of T, of momentum transfer, the data is best described by the models that require to have some subnucleonic fluctuations, which will be equivalent to say that we are sort of measuring some kind of gluonid hotspots. If I want to illustrate this with a cartoon, it will be something like this, that when we measure the incoherent process, we are measuring in this region kind of a smooth nucleons, but when we go to the highest T, according to these calculations, we should have this subnucleonic structure that now those photons are probing, and this was recently published, and we can discuss later if you want. Now, I just want to say that there are many other topics that I don't want to say. So there is a very nice paper also on looking now on other things, not just that, like looking at measuring angular correlations, polarization measurements, like doing femtoscale double-slit experiments where we can use this trick that we don't know who is originating this photon, which of the two, and that creates some ambiguity that can be translated on some angular correlations that is equivalent to kind of double-slit experiment where we measure, where the impact parameter that we measure through these neutrons is indication of the scale of this process. So there are quite a lot of things that I invite you to look into this program. Now, I just want to publicize just very quickly that in round 3, that we have right now at the Large Hadron Collider, one thing which is fascinating is that for the case of ALICE and also the LHCb experiment, it will be possible now to look at events without triggers with this continuous readout mode. And that's a great opportunity for this kind of physics because most of the things that we have done before was limited by the fact that we have to be very careful what kind of triggers we select. And this new system will really open the possibility to do all kinds of topologies and processes that were not possible before. I just want to also say that since I work on this, on the upgrades in the future, we have great upgrades like this ITS3M focal, this forward calorimeter, and it was recently approved. It's an interesting project that basically we try to, Okay, great. So it's a program that is trying to put a detector here at the most forward region. And remember, when we go to the most forward region is when we are the most sensitive to this kinematic region for saturation. And this is going to be located between 3.4 and 5.8 in pseudo-rapidity. You see here is a detector that has both electromagnetic and hadronic component. We have about 20 layers of these detectors. We have low granularity and high granularity silicon pads and map sensors, and the focal HCAL. And here you have a picture of this of the segmentation where we achieve this with the ALPIs that are used in the ALICE experiment. This program was approved, and there's been a lot of work and through this in a lot of prototypings. It's a project that perhaps you have heard in the past, but it has finally got approved by the LHC committee. and basically this year, a couple of months ago. And why is interesting? Well, it's interesting for measuring photons and also some jets in some kinematics. But in my case, I'm interested to use it for looking again at J size. The very beginning of my talk, I show that you can look at the energy dependence, even for the case of protons. And here you have two projections of what we can do with focal. This is the ratio of the models to fit to the data as a function of energy. Here on the left-hand side, you find the case where there is no saturation predicted. And here when we have considered models that consistent to the saturation signals like NLO, BFKL calculations. And what you find is that focal detectors should have the sensitivity to observe the deviation of this power law behavior, that is the signature of this, precisely in a region which is very unique. And I think that will have important discovery potential of this detector. There are several measurements, but this is another one. We can also measure the ratio of the cross-section of psi to S to J psi. And this is the measurements that we have from HERA at lower energies. And then when we go to the highest energies, particularly for this ratio, it's interesting that the saturation models produce a very different trend. Here is the case for linear and here is saturation. So it should be very clear also signature according to these models. Okay, in the 3 minutes I have left, I'm going to say, since I mentioned the want to publicize a little bit one of the activities that I'm 7 minutes. Oh, great. Okay. It is in the 7 minutes I have left. So instead of giving you, some summary about the physics, I want to use this time to advertise a program that some of you know and that we have is supported by the National Science Foundation, in particular the Office of the International Office of Science and Engineering, as a program called AxelNet. And a couple of years ago, we have come up with a proposal that is the IM-QCD, because all of us here are QCD, right? We're made of quarks and gluons. And so IM-QCD is the Inter-American Network of Networks. And this program, basically there are two phases. So we got a grant for the design phase of this program. And we are now preparing for the full implementation. And I want to mention this because I really want to see, more participation from, all of you and people participating. So one of the ideas of this program is a network of networks. So it's a community-driven effort, and we are trying to identify strategic partnerships across different projects and different networks. Develop these strategic projects, identify the needs and trends and synergies of the networks, and design activities for mobility across the region that can leverage resources on QCD research, and of course, heavily focus on supporting the next generation of researchers, students, and training. So when we say QCD, it's a very broadly defined in the way that we understand QCD for IM-QCD. So it covers accelerator technologies, theory, high-performance computing, software, particle detectors, and so on. And we had a kickoff meeting in December 2021, and we actually have Alina also giving a presentation. We have invited networks. This is an open network. Open network means that anybody is, welcome to participate. It's a bit different how most networks are done in Europe, where they are closed, most of them. Open means that future participation in networks is possible. So we have invited and our contacts with all the user facilities in the US, like the EIC user facility, JLab, RIG AGS, LHC, but also the ALAFNA, the SURA, and the Latin American Association, and so on. Great, thank you. And the Mexican Particle Accelerator Community, the one in Canada, and several ones in Brazil. Now, although they are not networks, we also have collaboration with centers. So we have the list, centers are considered partners. And so we have basically all the centers in the US on this kind of region. I just like from the center CFNS in Stony Brook, but also the ones in JLab and accelerator ones and the one in Latin America. And as I said, this is a community-led program. So what this network means in practice is that we support organization of workshops and conference and summer schools. This is done like we don't organize the schools and workshops, but we support the community to organize them. So that means if you have an event or workshop and you want to bring someone from the US to your meeting, or if you want to bring someone from Latin America or Canada to the US, we have funding to support this kind of activities. And also research visits. And now in the program we have now, this is the kind of path that can be done, but in the new program, NSF has actually changed a little bit the rules based on the feedback that we have given them. And the good news is that now it will be possible to actually support countries from, let's say, someone from Peru to come to Mexico, or someone from Mexico to go to Argentina. This kind of thing was not possible before, but that will be possible. And early career activities that are promoting communications, all these kind of things is possible. Now, just to give you an example of things that has been supported, so exchange visits. So through this program, we did not organize, but there's been an exchange program that was supported between Canada, Mexico, and the US on accelerator at JLab and Trump and BNL. And several research visits, a lot of activities also from theory, and some from UNAM has also participated. And we have call from proposals that has been done, but recently we have actually, it was last week, we had a summit where we invited people from the advisory board and some activities, and we are collecting a lot of inputs. If you register on our website, you will also get some link that you can submit and send us comments for the new proposal that we are preparing for the full implementation. So I give you here the link. So this is the link to the website, in-qcd.org. And we also have a mailing list that you connect. We will send this survey to get inputs on things that you would like to see for the next program, where we expect to have something like $2 million for exchange visits. That's the kind of thing budget that we are aiming to have. So we really expect hopefully a lot of activity happen. Okay, thank you so much.
Well, thank you very much for your talk. Questions? Well, I have one to begin with. I'm not an expert in this field, but what prevents, I mean, in all your sketches, you have a lead nucleus and a proton and a photon. Why do you only have one photon? Why do, I mean, your lead nucleus has a lot of protons, so why couldn't there be two or more?
Oh yeah, no, that's possible actually. We can also have photon. This is what you mean, photon events, interactions?
Oh, yeah. Well, yes.
Yeah, that's.
I don't know. A lot of photons can go back and forth. The time is very short, but having a single photon is just a special condition, I guess.
Oh yeah. That's an special.
Maybe there is a reason why that cannot be an obvious reason.
Yeah, no. This is also possible, but you know, and we have some papers actually related to this, also just emitting neutrons and also inclusive. But yeah, I try to focus only on this proton nucleus, but we do have results on that as well. Yeah.
Thank you. Some question from the audience? Oh, here, sorry.
I was wondering, you mentioned your forward detector, and in the same spirit as Arturo's question, what are the capabilities to detect the Auditorio, say, or pomerance with this detector? I know that the Auditorio has been claimed to have been detected by Totem. So do you have any prospects on that?
Yeah, okay, yeah, so I think it's an interesting question. So in principle, okay, the way that Totem was discovered was through this, the tagging of the protons, and then also looking at the momentum aspect. So we don't have like the tagging capabilities that CMS has. But there are some, as you know, there are some theory calculations that predict that another way to see the polymeron, the otheron, will be to look at the momentum transfer of the vector mesons like the J psi, and the momentum transfer at the very low momentum transfer has a very different behavior for otheron. This has been, you know, discussed. There are several calculations about this, but it has not been done because measuring the t-distribution, you require a lot of statistics, you know, to go to this very, very small momentum. Now, in the case of focal, at the moment, most of the, let's say, physics has been driven on proton-lead and lead-lead collision. So I haven't made the estimation of what luminosity will take to do it in PP, because, you know, at least doesn't run PP like all the time. Yeah. But I think yeah. Thank you for bringing this up, because something we should look, yeah.
One short question.
Arturo asked me to make it very short. So it's a very conceptual question that I never understood the answer, to tell you the truth. So you want to understand properties of the gluon, in particular, for example, in your case, saturation. Why shall I use a probe, like a photon, that does not couple directly to the glue?
Yeah. So yeah, so what you want to do is that the photon here is basically, as you know, the photon has a, you know, probability that will, you know, quantum mechanics will be, we have this dipole that can be a photon or it could be a vector meson, right? And so the thing is that we are looking at the interaction that leads to, like what I was saying, J psi, and the dipole size that is produced that corresponds to this vector meson is very different. So for example, the saturation scale, this is what we know, depends as 1 over the radius, right? So by changing the vector mesons, we have a great the dipole size, we have a great sensitivity to the target. So that's the idea.
Well, thank you very much again, Daniel. Now I call on Leonardo Gasques. Oh, here, hi, Leonardo. Who is gonna give us a talk entitled Reactions with Weakly Bound Nuclei Around the Coulomb Barriers. So we are coming back to more standard nuclear physics. This is work done at the USP, the USP.
Okay, thanks. Let me start thanking this kind invitation, and it's my first time in Mexico, so I'm really happy to be here. And as Arturo mentioned, we are going to slow down a lot the energy of the nuclei. So don't fall asleep. Like now we are going around the Coulomb barrier, so we move from JEVs to tenths of MeVs. I'm sorry. Let me see if this one works. Maybe this, okay. So just a brief outline. I will like spend a few slides in the motivation. So I will give like a small introduction about this this work. Then I will briefly refer to our facility, and then I will go to our scientific programs, and I will present some measurements and then some results as well. So the first question is, why are we still doing like a research with such kind of machines, right? It's low energy machines. And I could just say this is because this is the only one that you have in our lab. It's a good, I think this is a good answer, but we can do more than that. Right? So I think we still have to address like important questions like nuclear structure. We have heard a lot in this conference about this subject, and then in nuclear reactions, in nuclear astrophysics, and so on. So my contribution is going to be in this part of this program. And then, of course, like if we do research using this kind of machines, then we can develop into applications with like related to many applications, like in health, in medicine, and so on. So, okay, so we start from the very, very basic. Like if we have two nuclei that are sufficiently apart, then the force that these nucleons will feel is just the Coulomb interaction. Right? And then we know that when they get closer, then this interaction gets stronger and stronger. And then this is a repulsive force. But then if they get really close, like few centimeters, then the nuclear force starts to jump in this game. And then we can have something like this. So this is the strong force, and it's very attractive. And then it's a competition between these two. And then at the end, if we add Coulomb and the nuclear interaction, we are going to have this curve here. And this is what we call the Coulomb barrier. So at this point here we have the radius of the barrier, and then here we have what we call the Coulomb barrier. All right. So what we do, like in practice, like we accelerate like a projectile, like a nucleus, at energies around this. This is energy, right? So we use like projectiles and with energies around this Coulomb barrier, and then what we see mostly is what we call the elastic scattering. So the projectile goes through the target, and then it preserves like the energy and the mass. And then we can measure the projectile, like if we put like a detector somewhere here. And then although it's very simple, it's very useful for probing the nuclear interaction. So we are still doing this sort of experiments, and it comes for free in a real experiment. So then, if you want to describe this cross sections, we can like just use like what we call the optical model. So we have here the nuclear, a real part of the nuclear interaction, and then we add what we call the imaginary part that in principle takes into account all the other channels that are presently in those reactions. So we can use can pick any model. Like my favorite one is this one, the São Paulo potential, for a lot of reasons. Like I'm one of the authors of this potential. It's been used in the last 22 years, like quite a lot. Like it has a lot of reference, and it's very simple because it's a folding potential. And then here all you have to do is to plug the density distribution of each nucleus that participates on the reaction. And for this, we have systematized this radius and also the diffusions. So you just pick your nucleus, and then you can calculate the radius. The diffusion is defined. So we put in this equation, plug it here, and then you have the potential. So it's very, very simple. And gives very, very good results. As you can see here, like showing carbon 12 and nickel 58, several energies, and also silicon 28 on nickel 58, also several energies. And then the description is quite nice. Of course, here, what we do is we always say that the São Paulo potential is a free parameter potential, but of course, like we have there is a trick here. We have one free parameter that controls the imaginary part of the potential. So it gives like produce like this nice slopes here. So anyway, besides the elastic scattering, when we do a reaction, other processes may occur. In principle, like other processes occur. And then what we can have, like, so if I take like one example here, like lithium-7 on tin 120, then part of this flux will be related to what we call it an elastic excitation. So of course we can use part of the energy available in the system to excite either the target or the projectile, or in some cases like both simultaneously. And then the way we see this in our spectrum is we are going to detect this projectile with less energy if we compare with the energy of the elastic scattering, because it uses part of this energy to excite either itself or the target. Also, we can have, like we call it, the nucleon transfer. So in this case here, this lithium-7 could transfer one neutron to the target, and then we end up with another system, which would be lithium-6 and tin-121. But neutron is not the only possible. Like we could also transfer a proton on an alpha, triton, deuterium, 2 neutrons. Everything is possible. And then we can also have what we call a fusion, or in this case, complete fusion. And then, of course, like this lithium gets together with the tin-120, it goes through the barrier here, and then it gets trapped here inside, and then it will form like another compound. Okay. But then what we do in our lab is to study projectiles which are in fact weakly bound. So our preferred one is lithium 6 and 7, and then also boron 10. We could have a beryllium 9, but it's a bit more complicated for some technical issues that we don't like to address or we don't want to address at this moment. And then if you look here, like lithium 6, we could imagine that, or could suppose that the lithium 6 can be described by an alpha particle plus a deuterium, and then it's a cluster. And then the binding energy of this system is around 1.5 MeV. So this is much, much lower than the typically 8, 9, 10 MeV that we find in like normal nuclei. So that means that it has a larger probability of breaking during the collision. And then lithium 7 has slightly larger binding energy. And then if you go to boron 10, it's around 4.5. It's about like half of the normal cases, even though it's still interesting, like to do some experiments with boron 10, I'll show you. But then if this happens, then other possibilities come into part, and then we can have like what we call the sequential complete fusion. So that means that this, in case of the alpha, the lithium 7, like if the break is into alpha plus T, there is a chance that the alpha and the triton will be absorbed by the target. And then this is gonna lead to the same component as this one. And then it's very complicated. I would say it's impossible to separate this in the real experiment. So we don't see that. Lubier can calculate this, but we cannot measure it. And then we can have also, oops, let me come back here. We can have also what we call an incomplete fusion. So when part of this one fragment is absorbed by the target, could be the alpha or the triton, and then the other one flies away. And then we can have what we call a no capture breakup or elastic breakup, when both these fragments are not captured and not absorbed by the target. And this is exactly the one that we are most interested in. Okay, so this started a long time ago, this kind of program, this kind of research in Australia, like last century, when they performed several experiments using lithium 6, lithium 7, and also beryllium 9, and they were measuring the fusion cross-section. And then they just noticed that above the Coulomb barrier is already right about here. And when you go above the Coulomb barrier, then there was a suppression of the cross-section, a suppression with respect to the calculations. So they go there, they do like the best calculus that they can do it, and then when you compare with the data, something is missing here. And then they say this for lithium 6, lithium 7, beryllium 9, and then in 2007 or 8, I don't remember, we performed this experiment with boron 10 and boron 11. And boron 10 has a larger binding energy, and then we see exactly the same behavior. This is the calculation here, and this is the data. And then we just find a nice way for describing this, and then we said, okay, everything is solved. If the binding energy is lower, then this probability of breaking up is larger, and then it scales like this, and then we can move and do something else. But then they decided to do another experiment where they were interested in measuring this, the two fragments. So if they have here like a lithium 7, they were expecting to measure an alpha and a triton particle in coincidence. So they developed this very nice detector, which is called Balling. And they went below the Coulomb barrier. And then they just made this experiment, and they were very surprised with the results, because they could see here alpha plus triton, but then they also have seen alpha plus deuterium, alpha plus proton, and then alpha plus alpha. And then the conclusion was, well, this mechanism is not that simple as we were expecting, but then the breakup is followed by the transfer. So it's triggered by the transfer. So first we have a transfer of one nucleon, and then it breaks. Right? So like it's in this case, like if the lithium 6 transfer one neutron to the lead 207, then it's going to become a lithium 6, and then it can break into alpha plus deuterium and so on. Like if it takes a proton from the target, then it becomes like a beryllium 8, and then it breaks into 2 alphas. Okay, and then they started this program. They did a lot of measurements using heavy targets, and then this, if we moving from lead 207 to bismuth 209, you see essentially the same behavior. And then it's even more interesting because they put like a medium mass target, like a zinc 64, and then you see like the alpha plus triton just disappeared. So there is no alpha plus triton anymore. Like in principle, everything is transferred before and then it breaks. And then no one knows exactly why. So we have to keep doing this kind of research. And then I'd just like to mention briefly this experiment here. I think it's very nice. It was published in Nature 2 years ago. It was done by this Chinese group with the collaboration with some friends that you might know, like Marco Mazzocco and other guys that work a lot in this field. And then they could accelerate this boron weight with a proton halo nucleus. So it has deficit of protons. And then they use the same target as we have used it, like T120. And then you can see this is very interesting. Like this is the elastic scattering here. And then when they do like a one-channel calculation, like using like optical model and imaginary potential, then you can see like a dumping of the cross-section in this region here. This is the nuclear Coulomb interference region. And then they also could measure the beryllium 7 and the proton that comes from the breakup in coincidence. They measured only the beryllium 7, and then they measured both in coincidence, and then they plotted these results here. And then it's almost the same. And then they could do like CDCC calculations and describe very well this data. So then coming to our facility, we have a pelletron machine in São Paulo, which is 80 million volts. So that means that we can accelerate light projectiles like up to oxygen or fluorine with energies between 3 and 5 MeV per nucleon, not more than that. So this entire accelerator takes like 8th floor of this building. So everything starts here in the 80th floor. We have here like a SNICS, like a negative ion source. So then we prepare the sample that we want to accelerate. We do a mass selection here. Then we accelerate this using this our pelletron accelerator. So this is negative, so it's attracted by a positive potential that is set here in the middle of the accelerator tube, and then it goes into a carbon foil. Then it strips, so it loses electron, it becomes positive, and then it's reaccelerated. Then when it gets to here, like we do the energy selection, and here we can send the beam to one of these beam lines. So the work that I will describe is I have done in this beam line here, what we call it 30B, and it's neighbor to the Hebras that I think it's more famous. So this is a timeline of our setup. I think it's always interesting to show because this was 2016, almost 10 years ago. And then everything was very messy. We have only a couple of old detectors by this time. But even though we did a shot, like we did an experiment, boron 10 on T120 at 40 MeV. So this is about 5 MeV above the barrier, Coulomb barrier. And then we could get this very nice spectrum. So here we see the elastic scattering, and then you can see the first excited state of the boron 10 with around 700 keV. Then the first excited state of the T120, then the 3- of this, the excitation of this T120, and then we could also see some yields that are related to the neutron transfer. So we have this 1 neutron coming from the boron 10 to the T120, no, it's the other way around. We have 1 neutron coming from the T to the boron 10, and the boron 10 becomes a boron boron 11. So that was all we could do at this moment. But then we, of course, like we used this nice spectrum to convince our agency to give us more money to buy more detector. And then in 2018, we had our money for buying this kind of detector. So we have seen this before, like Luis Acosta showed us similar detectors yesterday. So it's this one is an SSD. So it's a 5 by 5 centimeter square detectors, and it has 16 strips, and it's only 20 microns. And then we bought also this pair detector, which is a wafer with 1,000 micrometers. And then if we combine these two detectors and put a mask in here, we end up with small 16 detectors, which was much better than the previous situation. So we have only one here by this time. And so if we choose like 1 pixel here, then we could produce this sort of a spectrum. This is much better than before, because now we have like E delta E. And so then we can actually identify all these processes, and we can also separate most of them. So we can see here the elastic scattering. And, this is also the elastic scattering. Then this is the elastic scattering on gold. Because usually what we do is we evaporate small amount of gold into our targets, and that's very useful for the normalization purpose, because at this energy is like any projectile on gold, it's Rutherford, and Rutherford we can control very well, like we can calculate this easily. So that's why we see like this ball here. So here we have boron 10 and boron 11. We have seen this before, right? This transfer. But then we can see like beryllium 10, which is very interesting because the boron 10 is converting into beryllium 10. Right? It's a kind of a single charge exchanger reaction that we don't know, we don't understand yet. Like we have to explore this more. We have been neglecting this for a few years. Then we see like beryllium 9, lithium 7, lithium 6, helium 6, which is very interesting, and then a lot of alpha particles that I expect. And then we could also see some events that are related to the transfer of one proton from the target to the projectile. So that was very nice. And then we can like have a better look in this spectrum. So here we have this elastic scattering here, transfer, beryllium 10, beryllium 9. And then if you see here, the projection of this into the E total, oh, this is into the mass, but it could be also into the delta E or E total, then we can see like the very nice separation between beryllium 10 and beryllium 9. So the resolution of this detector is actually very, very good. And then if we take only this beryllium 9, we see here, like if we do some exercise, take into account the energy separation of this T120 and the 1 proton, then we can be convinced that part of these yields are actually related to the breakup of the boron 10. So the boron 10 breaks into beryllium 9 plus proton, and then it would be very useful, very interesting to measure both in coincidence, not only beryllium 9. Okay, that gives us some information, but this is not enough. So then just to show you the quality of the data, we see here the elastic scattering, boron 10 and T120. So this is normalized by the sigma Rutherford. So here we have essentially 1, and that's because only the Coulomb interaction comes into play at these forward angles. And then here we can see the manifestation of the nuclear force. So as I said, this is was measured at 40 MeV, so it's 5 MeV above the barrier. So as the elastic cross section drops by quite a lot. This is 10 to the minus 2. So that means that you have to wait long time to get these cross sections with such precision. So it takes like several hours or few days. And then everything looks very good. Like we can use the São Paulo potential. We can do a couple of channel calculations. We cover as many states as we can, as we know. And then we describe very well the elastic scattering. And then also we can describe simultaneously the elastic cross sections. Right? So this corresponds to the first excited state of the target. This is the 3-. This is the first excited state of the projectile, and so on. So everything looks very well controlled. But then, very recently, we did another experiment trying to cover this angular region here that was missing in the first measurement. But we had a problem with our machine during this measurement, and then we could not measure this at that moment. So then we did it a few weeks ago, and then this is very interesting again. You see, like you see this dumping. This is exactly the same curve as this blue one. This is the same energy, but then when we cover this region with this new data, we can clearly see this dumping in the Coulomb interference region. So it was there. And I think this is related to the nature of this projectile, like it can break up. So it has almost the same behavior as boron weight. And then we can continue. And then if you have a look here, this is exactly the same reaction, but taking at a 37.5 MeV. So it's only 2.5 MeV above the Bayer, around 7 to 8% above the Coulomb Bayer. And then we see again this dumping. And then if we compare with boron 11, essentially in the same energy, then this is very clear. You see, this is the yellow points related to the boron 11 on T120, and then we don't have this dumping. And then if we compare with boron 10, the dumping is there. And so this is essentially the same energy with respect to the Bayer. And then boron 11, it's a normal tight nucleus, right? There's binding energy is 8.5 MeV around it. Anyway, so then we have performed a lot of reactions using lithium 6, 7, boron 10, boron 11. But then from 2016 to end of 2022, beginning of 23, we were quite bored of doing this program. And then we decided that it was time to do exclusive measurements. So now we went to measure like the fragments in coincidence. But then we have here a list that the reactions that we want to study. We have done a few measurements in some of this, and then I will show some preliminary results. So for doing this kind of experiment, then we have to improve our setup. Then one detector is not enough. One detector, large detector with this mask is certainly not enough. So we need like detectors which have like large granularity and then a larger geometric efficiency. Otherwise, we cannot measure these two particles in coincidence. So we decided to dismount everything, and then we mount new setup. So we replaced basically everything that was inside it. So we have now new plate, a new target holder, but this is not critical. Of course, like what we did, like the most important changes related to our detection capability. So now at the moment we have two detectors like this one. So we put in the middle of this SSD and the pad another detector, which is also a 16-strip large area SSD, but it's much thicker. So rather than having 20 microns, it has about 400 microns. And then if we combine these guys, we end up with 256 pseudo telescopes. And at the moment, we have two of these working. So then every small square like this is 3 by 3 millimeters is one detector. So this gives us the proper granularity that we needed, because then we can have like one fragment coming somewhere here and the other fragment coming somewhere there. And so then we started this game. And then just to show you the quality of these detectors, like it has a very nice energy resolution. We did a quick measurement using a lithium 7 projectile. Now we prepared a T119 target. And then we went around the Coulomb Bayer, and then we can see, apart from the electric scattering, we can see the inelastic excitation, and then we can see also alphas, helium 6, which is again, which is related to the proton stripping. And then we can see here a lot of light particles like proton, deuterium, and tritium. And many of these particles are certainly related to this breakup process. So here we only measure this inclusive particles, so we didn't measure this both in coincidence. And the reason is because we have to prepare like a much thicker target for for measuring this process, because the probability is quite small, quite small. So then if it takes like a lot of days, and even though we need like a much thicker target than this one. So actually what we do now like is we try to prepare two targets, like one very thin and the other one very thick. And then we do this kind of measurement with the thin target, because if you use the thick target, then we are going to mess this nice energy resolution finishing. And then we replace this by a thicker target, and then we do the breakup measurement. So this is in our plan for next semester. But then we also did the same for boron 10, and then we see here this nice spectrum. So maybe I should say that this is energy, total energy, and the energy delta E, the energy lost in the first detector. And this is much nicer, you can see here. And this is only channel. So this is energy per energy loss. So that's why it's not so nice as the other one. But even though we can see the elastic scattering here, and then a lot of other process that we have to go and look better. But then what is really interesting in this case is this is related to one of these PCO detectors. But then what we can do is to sum all of these pixels, right? And then of course we're going to mess a lot with this nice spectrum. And there's a reason for that. This delta E detectors, the Micron, that is the company that produces this detector, they claim that this detector is 20 micrometers, but in fact it is not. I mean, it's completely non-uniform. So if we have to characterize this detector before using it, we have done this, it's a lot of work. And then we can see that actually this thickness varies from 14, 15 micrometers up to 27, 28 in the same strip. So then if we don't take this into account before adding pixels, then we are going to end up with something like this, which is completely useless. But in this case, it's not so useless, because the reason why we did this was the statistics of this one pixel is not very high. But then if we add 200, multiply this by 256, then we end up with a much larger statistics. And then we can check for the possibility of having this produced these particles in coincidence. So then this is related to lithium 6. So we can put a gate in here, and then we can plot only the particles that came into coincidence with the particles that are inside this area. And then if we do this, then we end up with, of course, the lithium, and then a lot of alpha particles as we were expecting. So that was just to a proof of concept to convince ourselves that we are in the right track. And then we can do exactly the same for boron 11. So this is the kind of spectra. It's very similar to the boron 10. Then if we add all the pixels, we get here now in lithium 7 events, like boron 11, we can describe as a core of lithium 7 plus an alpha particle. And then when we look into here, there is practically no alpha particles in coincidence with the lithium 7. So probably the probability of the beryllium 11 to break up is, as we know, like it's much, much smaller than the boron 10. So what we have to do now is to find a clever way for going from this quantitative picture to convert this into cross sections, which is much more complicated because it involves a lot of simulations, and I don't think it's going to be simple. So just to summarize, what I have shown that we investigated several reactions with weakly bound projectiles at our lab, and then I show only few cases, but I can say to you that all in all, like the couple channel calculations, it provides like a reasonable description of all our cross sections, and then also like this the simultaneous description of this many process are very good benchmark for this nuclear potential models. It's very complicated. I mean, it's very simple to describe the elastic scattering. You can do a lot of mathematical tricks, but then if you want to describe all this process simultaneously using the same interaction, then it's not the thing, like it's much more complicated. But I think what's really important is that we have to continue developing the instrumentation. This is extremely important, and then it must go on. And then, of course, like students are very welcome for joining our research group. So thanks a lot for the attention.
Yes. Okay, well, thank you. And questions? There. Luis.
Hello, hello. Thanks for this nice presentation, Leandro. My question is regarding your targets. You can produce your own targets. Well, you speak about this gold film that you could put inside. How you control this? This system is part of your lab, it's another group, or how do, because this is very important in the case of normalization, and you can avoid to use a morbing time to, in the case of some kind of Rutherford regime, no? We can say.
Yeah, no, we are very lazy, so we have a technician for taking care of this stuff. So we have a lab where we can produce those targets. We cannot do every target because we have, at the moment, several limitations, like our main evaporator is just broke, and then apparently it's very difficult to put this to work again, so we have to buy a new one. But we can do some easy targets, like T is a very easy target. And then for evaporating gold, it's very simple, like we can do this in few hours, like this is not a problem.
Okay, thank you. I have a question, well, a suggestion rather. When using this new type of detectors, you can actually detect the two simultaneous alphas from a beryllium mate, and you can reconstruct your beryllium mates. Yes. So that's one thing that you can do, and even. I understand each one of your pipes in there is a delta E detector, or not? These are telescopes?
Yes, yes, these are telescopes. So this is, I think I should go back. So these are telescopes, and I think you can see it here. Right? So this is, this is the first.
That I understood. That you have delta E and E on those.
You say the other ones. Like
the other ones are also.
Then it depends. Like we can mount like BIPs, like small telescopes in here, or we can mount a single detectors. Actually, we have around 7 or 8 telescopes available at this moment. So then what we do is we mount a few telescopes and few single detectors. If we go to very, very forward angles, then it's better to have a single detector for serving as a monitor. And then we try to cover some key angular regions using this pips here. And I think this is very nice because it's since they are very, very much simpler like to operate, then it's always nice to overlap like few angles of the using pips and this strip detectors, because then we can compare the cross sections and see if we are not doing something very stupid.
Well, I said that because on delta E telescopes, I'm coming back to the beryllium mate.
Yeah.
2 alphas going through the same delta E simulate a lithium-7. This was
no, that we can actually separate. Like if we have seen this in if you let this for long hours, then we'll see eventually 2 alphas coming into the same pixel.
Yes.
But then we can separate them from the legion because it goes with the delta E goes with Z squared.
Yes.
So then it's very simple. Like it goes to another spot.
Okay.
We don't get much of them, but then
no, you can.
We get quite a few. So this is something that's in our, of course, like it's our program. Like in principle, we can measure any 2 charged particles in coincidence. Actually, we tried it 3. a few weeks ago with our colleagues from Seville, from Spain. But I think that was too much. Like they tried like carbon 12 and carbon 13 in zinc 64. And the idea was to try to trigger this breakup of the carbon 12 into 3 alphas. And they want to go close to the Hoyle state and see if they could break. I mean, we can see like 2 alphas, that there are a lot of 3 alphas. It's much more complicated.
It's more complicated. There, Maria Esther. Oh.
About this problem with your non-homogeneous delta E, it's just a correction that you need to do once, no?
Yes.
Yes.
Yes, we do this once. So we got a very clever master student, like he's a master of Python, and then he developed many scripts. And now everything is easy. We have to do only once. And then also we have to be sure that the angles that we think that we are measuring are correct. So for that, we do like a couple of Rutherford experiments, and then we can check if the solid angle, the angular position is all right. But then once we get this done, we just have to preserve the script, and then we are going to be safe.
Each delta E will be different.
Yes, this is the problem. So each delta E is extremely
always
different.
the same.
Yeah, and then also we have a dead layer in the entrance and the exit of these very thin detectors. And then if you really want like a very good energy calibration, we have to take this into account. But then if you ask the company, that you say it's something around 8 to 10 micrometers, 0.8. But then when you do your measurement, you get 0.3, 0.4, like it depends. So we cannot rely on this information.
They should refund you part of what you paid.
Oh, that's a nice
Because
idea.
you bought a given thickness, no? And they gave you a variety.
Yeah, this is normal. Like they are doing this for many years. Like everyone knows that.
It always happens.
Yeah, it's very expensive, and then anyway.
Another question? Well, if not, thank you very much. Okay. We are